Hi and welcome to John's Maths Book. In this video, we're going to be looking at the center of mass of a circle with a segment missing. If you like the video, then please hit the like button and I'd be delighted and honored if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. In the last video, we looked at defining a region D, shown here as the red and green shaded areas, in terms of integrals using the polar coordinate system. I've included a link to this video in the comments section, which I recommend you watch first. In this particular video, we'll evaluate the integrals and determine the center of mass, also known as the centroid, as the region D is assumed to have a uniform density. Once we've evaluated the integrals, we'll include some values for A and B to check our answer. To recap, the double integral of dA shown here will sum up the infinitesimally small pieces of area and give us the total area of the region. And if we take the double integral of x multiplied by dA, as shown here, this will give us the average value of x. If we divide this by the total area, denoted by A, we get the center of gravity or center of mass of the region. This is denoted by x bar. So let's now evaluate this double integral here. This will give us the average value of x over the region. Starting with the inner integrals, we have the integral from r equals 0 to r equals b divided by cos theta of r squared dr plus the integral of r equals 0 to r equals 2a cos theta of r squared dr. In both integrals, the antiderivative of r squared is r cubed divided by 3. Evaluating r cubed divided by 3 between the limits, we get b cubed divided by 3 times cos cubed theta plus 8 times a cubed multiplied by cos cubed theta divided by 3. And now if we work on the outer integrals, but before doing that, we multiply through by 2 cos theta in each case, we're left with 2b cubed divided by 3 multiplied by the integral from theta equals 0 to theta equals alpha of 1 over cos squared theta d theta plus 16a cubed divided by 3 multiplied by the integral from theta equals alpha to theta equals pi by 2 of cos to the power of 4 theta d theta. Starting with the first integral, we can replace 1 divided by cos squared theta with the trig identity secant squared theta. The antiderivative of secant squared theta is tan theta. So evaluating this between the limits of alpha and 0, we get 2b cubed divided by 3 multiplied by tan alpha. So now let's work on the integration of cos to the power of 4 theta, which is our second integral. To do this, we need to rewrite it. So we can rewrite cos to the power of 4 theta as cos squared theta multiplied by cos squared theta. And we can write cos squared theta as 1/2 into 1 plus cos 2 theta. If we multiply this out, we get 1/4 into the bracket of 1 plus 2 cos 2 theta plus cos squared 2 theta. Now using this trig identity that we use to rewrite cos squared theta, we can write cos squared 2 theta as 1/2 into 1 plus cos 4 theta. And expanding this bracket, we're left with 3/8 plus 1/2 cos 2 theta plus 1/8 times cos 4 theta. So now we can replace the integral of cos to the power of 4 theta d theta between the limits theta equals alpha and theta equals pi by 2 with 3/8 times the integral of d theta from theta equals alpha to theta equals pi by 2 plus 1/2 times the integral of cos 2 theta d theta between alpha and pi by 2 plus 1/8 times the integral of cos 4 theta d theta between alpha and pi by 2. So the antiderivative of 1 times d theta is theta, and that's multiplied by 3/8 to give 3 theta divided by 8. The antiderivative of cos 2 theta is 1/2 sine 2 theta multiplied by 1/2 gives sine 2 theta divided by 4. And the antiderivative of cos 4 theta is 1/4 sine 4 theta. Multiplying this by 1/8 gives sine 4 theta divided by 32. And all three need to be evaluated between theta equals alpha and theta equals pi by 2. So now if we start by substituting pi by 2 in for theta, we get 3 pi divided by 16. And if we substitute pi by 2 into sine 2 theta, we get sine of pi, which is 0. And similarly, where we have sine 4 theta and we substitute in pi by 2, we get sine 2 pi, which is also 0. And now subtracting what we get when we put in a value of theta equals alpha, we have minus 3 alpha divided by 8. And here we have minus sine 2 alpha over 4. And here we have minus sine 4 alpha over 32. If we now multiply our result by 16a cubed divided by 3, we're left with pi a cubed minus 2a cubed alpha minus 4/3 a cubed sine 2 alpha minus sine 4 alpha divided by 6. Now, to check our work, we can add values for a and b. We know from the previous video that b must be greater than or equal to a and less than or equal to 2a. So if b is equal to 2 and a is equal to 1, then this still satisfies that inequality. If we put in our value for a is equal to 1, we see that we now have a circle centered at x equals 1 and y equals 0 with a radius of 1. As b now has a value of 2, we now have a complete circle without a segment missing and angle alpha equals 0. As we saw earlier, as this circle has a uniform density, its center of gravity or center of mass will be given by the double integral of x dA divided by the total area. Intuitively, we can see that it's symmetrical about the x-axis, and therefore its center of gravity will be at x equals 1 and y equals 0. So let's now plug our values of a, b and alpha into the integral, divide this by the total area A, and see if we get a value of 1. The area over this circle is pi r squared, where r is equal to 1, so the area is equal to pi. So 1 over the area is 1 over pi, and then plugging the values for a, b and alpha in, we have 16 over 3 times tan of 0 plus pi minus 2 times 0 minus 4/3 sine 0 minus sine 0 divided by 6. So tan 0 is 0, so that cancels out. 2 times 0 is 0, that cancels out. Sine of 0 is 0, and sine of 0 is 0 again. So we're left with pi. So therefore we have pi divided by pi, which is equal to 1.